Hello everyone and welcome back. So now we're going to start doing some examples. So what are we doing exactly? Well, we have a beam. It's set to an equal 375 Newton meter bending moment, as shown right there. And the cross-sectional dimensions are given down here. And it wants us to find a lot of stuff. One, the centroid location, as well as the moment of inertia. Second thing, the bending stress at point H. Okay, what's the bending stress at point H? Where's point H? Right there. And finally, the maximum bending stress produced in this cross section. What's the maximum bending stress? And whether it's tension or compression. And in this case right here, we're going to have compression above, because this is squishing it in, and tension below our neutral surface, or below our centroid. So, I'm going to do this one with you. Though this is a video, so you can pause and do whatever you want. But I'll do this one with you. Next time, though, you're going to try it on your own first. So here we go. Let's just jump straight into it. Now, the first thing we need to do is to calculate our centroid. And we're going to be referencing the bottom of our U-shape. Okay, so we break it into three different shapes. Left side, right side, and that bottom flange. We calculate their areas, which are not too difficult because they're all rectangles. And we calculate their distance to their centroid from the bottom. Distance to their centroid from the bottom. So we have 25, 25, and 4. We multiply all these things, and then we add them all up. Because our centroid equation is going to be y bar is equal to the sum of their centroid times the area. So the distance to their centroid times the area over the sum of the areas, which comes up to be 19.67 millimeters from the bottom. So going back a little bit, that's going to be 19.67 millimeters from here. Okay. Now that we've done that, we can calculate our moment of inertia about the z-axis, which once again is going to require us to have a big old table. Now, this comes from your textbook, okay? That comes from your textbook. It's going to be base height cubed over 12 for a rectangle. And there's a whole appendices or table for a lot of those equations. Now, that is just the base moment of inertia for that shape, as if acting as if its centroid was located at the actual centroid. However, all these shapes, they're not actually centered on the centroid. And so therefore we have to use our parallel axis theorem to figure out how to correct that. So that's where this d squared a comes from. So first off, we use that equation to calculate the moment of inertia. We do that for all of them. And then we figure out what the distance is from their centroid to the actual centroid. Their centroid to the actual centroid. And then once we've done that, we can begin to calculate everything else. So this is the distance for the centroid to all those places. Our centroid was located at, going back just a little bit, 19.67 millimeters. And so for the left side and the right side, they were 25 millimeters from the bottom. So 25 minus 19.67 is equal to 5.33. If you're wondering about negatives or positives, in this one it doesn't matter because it's d squared a. You're not going to have an imaginary distance, and so that negative sign is going to disappear. So we calculate this correction term, and then we add them all together. We add them together to see what our total moment of inertia is, and it's right here. So we add all of the moment of inertia about their own axis. Then we add these correction terms, the parallel axis theorem, and when we've done that, we get our total moment of inertia. Okay. So we have the centroid now, we have the moment of inertia. This is going to be a very common thing. You're going to see it every single time. So get used to making these tables. This table is probably the best method to do it because it's just a good way of note keeping. You never forget what you were supposed to write down. Okay, now the section modulus. So the moment of inertia over the distance to the top or the bottom. And we're looking for the one that is the smallest. We're looking for the one that is the smallest. Reason, because that one will have the greatest stress later on. And so the greatest section modulus will be for the top. It's saying that that's going to have the greater stress. And then if we want to, we can finally start calculating the bending stress at point H. Now, for point H, it's down there at the bottom. We have to figure out the distance y to that point. And so since that is going to be 8 millimeters right here from the bottom, and my centroid is 19.67, I can then see that that's going to be negative 11.672 millimeters from that point, so going down. Then I know my normal stress equation is simply the moment, which is given to us in the problem statement, times my distance, times the moment of inertia. I'm converting everything to millimeters just to remind myself, because that 1 Newton per millimeter squared is equal to a megapascal. It's that nice, wonderful conversion that we've done like 1,000 times. Okay. And finally, what is the maximum bending stress? Well, the maximum bending stress occurs at the greatest distance away from my centroid. So that's actually for the top, because it's 30.3 millimeters to the top, and only 19.6 to the bottom. Or we could also say the one with the smallest section modulus. Either way works. And so what we get is we'll have a negative 44.14 megapascals, which happens to be compression, so we can just write 44.14 megapascals compression. We know that's compression because of the bending moment. It's pushing in at the top, and so I have compressive stresses. It's pulling out at the bottom, and so I have tensile stresses. Okay, that's it for this one. Thank you for listening. I hope this helps you, and I will see you all next time. Please, please, please look over that table method, master that, because that is a complete lifesaver for these kind of problems. Okay, see you later. Bye-bye.